Hi, welcome back to Book Club. We're in linear algebra right now, which is ultimately how all computers solve real problems. We'll talk through the methods of how you convert physics equations, usually differential equations, partial differential equations, these phenomena. We'll talk about how you convert that from derivatives and integrals and whatever those equations are into algebra. That's part of it. That's called discretization. But then once you have a matrix, and you're now solving for your unknowns. And again, your unknowns, using a computational fluid dynamic example, your unknowns could be the velocity, pressure, temperature at a given time. You're ultimately inverting a matrix to solve those. And so you cast your entire problem into a matrix, some matrix of n by n size times x, which has n unknowns, is equal to b, which is some right-hand side. Okay. Now, if you're lucky when you're doing some of those discretizations, maybe you can only invert this once and then reuse it. So we'll talk about today kind of some of the ideals. Remember that this is to fully invert this thing is an order n cubed operation to invert it. So we'll talk through some different methods, and ultimately we will eventually get to things that are order n methods. And this is really the rubber hits the road in terms of computing. And so the first thing we're going to walk through is called pivoting. Okay? Pivoting. So we'll use a very easy example. Pivoting. Now, this is just a simple 2x2 matrix. It's all you need to show this problem. So imagine my matrix with 0.0003 and then 3, 1, 1 times x1, x2 is equal to the right-hand side 2.0001 and then 1. So again, this is two equations, two unknowns, so it's 0.0003 times x1 plus 3 times x2 is equal to 2.01. That's equation number 1. Second equation is x1 plus x2 is equal to 1. So I know x1 and x2 both have to add up to 1, and honestly, the exact method, if you just happen to look at this, we'll kind of cut to the end here. The exact method is x1 is equal to 1/3 and x2 is equal to 2/3. Right? That is the exact answer. So they both add up to 1, check, and then this 1/10 of a thousandth times a third is 1,000th plus 3 divided by 2 plus 2 is equal to 2 and 1/10,000th. Okay, so that's the exact solution. But remember, our computers actually don't store 1/3, right? That's a fraction. Our computers will store that as 0. Maybe it's and we're gonna be funny here. So maybe I have a computer that it only has 2 digits of accuracy because I'm not carrying 32 bits. I'm carrying maybe 4 bits or something like that. So depending on how I store this in a computer, how many digits. You see where I'm going with this. This is 67 or 0.667 or 0.6667 or anyways, depending how you store this stuff, it'll actually impact your method, okay? And it's because in the end, when you are the first step of this method, so if I'm inverting this method, I'm going to come down here, so give myself a little bit of room, I'll come back to this. The first step is to zero out this thing. And so what are you multiplying by to zero that out? Well, if you do the math, you end up saying the top equation is x1 plus 10,000 x2 is equal to 6667. That's actually your top equation. And so when you're solving for, and then it's 0, in fact, let me do this as a matrix. So that's 1 plus 10,000 times x1, x2 is equal to 6667. And then this is minus 6666. Gosh, that got messy. All right, 1, and then plus 10,000, and then this bottom is 9999. Okay, so when we do the human method and we make this 0, we're dividing by 0.003 to make 1, and then multiplying by, and then subtracting it from this equation to get 0. And so this is what you end up getting. So this is now, and the, sort of the matrix conversion step, this is where we've gotten to. And that's, so Gus, I know. And so then the final step is then x2. Okay. This problem is fine. X2 is basically equal to 2/3. But then it's actually solving for x1. And so if you actually go right down, then what you do on a computer is x1 is equal to 2.0001 minus 3 times however you're storing this divided by 0.0003. Okay, so and because order of operations and things like that, the first thing you would do is do 2 divided by 3. You're going to store it in one of these methods here, and then you're going to multiply it by 3, and then you're going to subtract 2.01. So if you actually walk through each one of these, 2 digits, 3 digits, 4 digits, and I didn't give myself enough room here, my apologies, but what I wanted to show, and maybe let's do it right here in the column. So this is your error. You're going to get, basically 1,000% error here if you only store 2 digits. Right? Let's see, how do I do this in not so trashy of a version? Okay, give myself a little bit more room. And I'll erase this here in a second. You guys are seeing the action and work. All right. There. So now I've got myself a little bit more room. If you actually solve for x1 here, this is, you would get minus 3.33. Like, it's not even close. It's not even close to 1/3. So it's massive error. And then this is then 100% error. This is, 10, 1, and then finally 0.1. So as you keep storing more digits, you'll be able to compute this more accurately. Now, imagine if we flip this matrix around. Imagine if step 1, and I'll give myself more space here. Now imagine if step 1, I actually took this matrix and I said, I'm going to put the biggest one up front. I'm going to look at the current column I'm on and flip it. So if you then numerically solve 1, 1, 0.0033 times x1, x2, it's all the same. It's literally the same two equations. And this is 1, and this is 2.0001. Okay? And you repeat this whole process, you'll end up getting, x1 is equal to 1 minus x2, right? So you multiply by this, by the 3, like this is literally, and so however you store 2/3 in here, then this is how you compute it. And so before you had a problem here with basically a small difference of 2 big numbers, and here you don't. Okay, and so it's really, if you look at this, because what's happening here is you're, even depending how you store 2/3, just look at it. 3 divided by 3 is 2. So this is, you're basically going 2.001 minus 2. So that's a very tiny difference. And then, so depending on how accurate you store this initial step, because it's a tiny difference of 2 big numbers, really matters. But here, it doesn't, because this is 2/3, this is 1. They're far enough apart. So literally just reordering this, pivoting, you get a massive difference. Okay. There are other matrices, and so I'll switch back to green. So I'm going to show you a couple more things. There are other matrices if your discretization, and we'll show some of this, gives what's called a tri-diagonal matrix. So this is basically, we have values on the diagonal and you have values on the off diagonal. So finite difference will actually give you this, and that'll be the example we'll end up using. Then this is solved in order n. It's basically, I can be smart about this and just basically kind of crunch my way along. So as opposed to inverting in order n cubed, this one is inverted in order n. So super fast. So this will be an example of, pivoting is an example where the order of operations drastically changes your accuracy because of digitization. So this is a problem of digitization. We still have compute time. This is a problem of discretization. But this one, if this happens to be my matrix and I'm smart about it, then order n is so much more faster than order n cubed. So this is then just being smart about your algorithms. Back to the algorithmic speed up. Okay. And then I may walk through this a little bit more in detail next time. I think I'm running out a little bit of room and getting a little too worried about it. So what we'll come back and do next time is in a couple different methods. But ultimately, what we end up doing, and I'll show you that really what we did here in the process was we actually split matrix A into a matrix that is values, and then the lower diagonal is filled and 0 on the top, times an upper diagonal. The values on the top times 0. That will actually show that this is what we ended up doing. And so if this is the case, then this is called LU decomposition. What you actually want to do is don't just do these side steps. If you store it, we'll come back and we'll show some of that. Okay. And then there's a version where you also combine LU decomposition with pivoting. So I'll come back and show that, right? And the reason this is important is actually if you split this, I'll kind of give the punchline and I'll repeat it next time. If you split this is order n cubed to split it. Okay, but now if I've saved that on my computer, right? In fact, you're going to see that this is basically ones on the diagonal. If you save it on the computer, in fact, you can save it very compactly as opposed to saving the zeros. Every time you redo it, so this is ax equals b. Every time you need to redo it, so if I gave you a different b, because maybe this is a different time step or something has changed, back to the other example before, if I change the masses, every time you then solve, so this is once to split it, and then the solving step only takes n squared. And so if you're doing something, even if it's MATLAB and it takes a little while to crunch it, you may think about Python, whatever it is. You actually may think about all those methods have this LU decomposition. You may think about taking your matrix A. If your matrix A is never changing, do the LU decomposition, save it, and then if you look up LU decomposition in both MATLAB and Python, they'll talk through how you do this, how you save it, and then ultimately you then call the method and said, here's the L, here's the U, here's my new B, give me the answer. So all of this algorithmic speed up really shows up. So again, we have the problem of discretization of your problems, and where you can have different algorithms, and then you have the problem of digitization, and we've got to take care of both things as we're doing this. So we'll come back next time. We'll talk a little bit more about LU decomposition, one called Cholesky factorization, and then we'll kind of keep moving on. So we'll see you next time. All right, welcome back to Book Club. So last time I was going through, actually not last time, I'm merging these two videos together. I realized the LU decomposition wasn't too much more to add. I was just running out of space. So let me finish up here with the kind of clean whiteboard. So LU decomposition, I was saying that your matrix A, you're actually going to convert to LU such that AX is actually the matrix L times a matrix U times the unknown vector X is equal to B. Okay? And so that's the decomposition we're going to do. In fact, what I'm going to show you is that if this was in an upper diagonal, so this would be unchanged. So this is A11, A12, A13, and then ultimately, what we were doing, even in the human method, is we were zeroing out this term, and then let's call this A22 different, and this is A23 different, and you kind of work through this. So I'll just zero it out, and this is A33 different. Okay, so, and this left one is actually ones on the diagonal, and then zeros in the off diagonal, and then this, we'll say F21, F31, F32. So, goodly, these factors, that's off the screen. Okay, moving to the right a little bit. As you can still see here. Okay, there we go. Ones on the diagonal, F21, F31, and F32. Okay, so if F21 is actually equal to the original, this would have been the original A21 divided by A11. So watch what happens if that's the case. If you do sort of the row times, ones. So if you work this out, what that would give you, again, you do 1 times this, because it's 0, 0, that gives you A11, okay, A12, 1, 0, 0 times 1, 3, 1, 3. So it basically doesn't move the top. The top row is unchanged. And now the bottom one, F21 times A11 plus 1 times 0 plus 0 times 0. Okay, so this is simply F21, which was this, A11. It's divided by A11, so that's 1 times A12. Well, that was just this, okay? Now, before we do A22 prime, just when you go back and you actually figure out, like, hey, what was A22 prime? It was actually A22 prime, because we actually started with A22, and we were multiplying the top row by this factor and subtracting it. That's how we got this to be 0. And so that is actually then A12 times the factor, and the factor is A11 times A21. So if you solve for A22, that's actually A22 prime plus A12 times A11, A21. All right, so if you do this rote multiplication, F21 times A12, well, that's that, plus the new one. See, that actually fully undoes it. So this is indeed A22. Okay, and then you just rinse and repeat, and you convince yourself this is absolutely true. So this gives you right back the full matrix that you had. Okay, so this LU decomposition is nothing other than putting ones on the diagonal, I'll stand it a little taller, and then storing this step that we were doing in the normal Gaussian elimination. You are actually storing it here. So it's a storage method, but you're basically storing it, and then when you're solving for it, when you get to this point, and by the way, that the right-hand side changed as well. So at the very end, you then solve this thing by saying, okay, I'm here, and I actually have A33 prime times x3 is equal to b3. All right, so you just undo it, not undo it. You now have x3, and then now that you have x3, it's that whole backward substitution. And so really, the LU decomposition is actually what we did previously. We're just storing it. And so for the storage, in fact, because this is ones, if you're worried about memory, you could actually store this, the off diagonals, into this term and just kind of bookkeep it, which is what those algorithms do. Okay, and so what this lets you do, if you actually store it like this, then when you come back and you just do this back substitution, that's what I was saying. It only takes order n squares to perform all of this back substitution. You get x3, then you get x2, then you get x1, and away you go. And so that way, if you get a new b, you could just repeat it. And so the only other one to mention is this one called, so this is LU decomposition. And then there's a special case where that matrix is actually the transpose of itself. So that's what transpose means. You just take this matrix and flip it on its diagonal. And so this is Cholesky. Okay, and I think the only thing I want to say about the Cholesky factorization is this only happens, and you read this, and we'll show this later. You have to go do eigenvalues first. But this only works if A is positive, definite. Right? And what that means is that eigenvalues are all positive. So we actually, I will teach this. The book I'm kind of following just mentions this briefly, and it's like, it's not helpful. Like, until you actually show what an eigenvalue is, which is where we're going, then you would come back and do this. And then what's the value of this? It stores by half. Okay, you don't actually have to store the L and the U, you just store the U. So it's really almost the same thing. Sometimes it's confusing when you see it in the book. That wait, is this? What is this? How is it different? It's not different. So that's LU decomposition. You can see why I was getting worried that I didn't have enough space to really show this well. And so we'll see you next time. We'll dig into the next topic.